In this video, I introduce a vector-quantized variational autoencoder for discrete representation learning. Autoencoder is a generative model that can be used to learn representations of input samples or reconstruct the input samples in an unsupervised fashion. Autoencoder trains a neural network to reconstruct a sample as close to the original input as possible through the latent representations learned by his encoder from the input sample, as shown here, this encoder and this decoder. Variational autoencoder uses a probabilistic distribution to replace the latent variable in the latent space, as shown here. The reconstruction loss measures how well the decoder reconstructs the input from the latent representation, while KL divergence measures the difference between the learned latent distribution and prior distribution. Vector-quantized variational autoencoder is an improved variational autoencoder model by incorporating vector quantization into variational autoencoder to learn discrete representations through a codebook, as shown here, in an unsupervised fashion. Suppose that E is a latent embedding space with a size K, where D is the dimensionality of each latent embedding vector EI. VQ-VAE projects the latent representation ZE produced by the encoder to the nearest neighbor EK, which is then fed into the decoder. The posterior categorical distribution Q probabilities are defined as one hot vector, as shown here and here. If the prior P is uniform over the sample category, KL divergence is a constant. ZE is a map onto the nearest element EK. No gradient computation is from ZQ to ZE. The straight-through estimator copies gradients from decoder input to the encoder output. The overall loss function is defined as sum of three terms, where the stop gradient SG is identity at the forward pass and his derivative is 0 at back propagation, which constrains his operand to be non-updated constant. The decoder optimizes the first loss term, and the encoder optimizes the first and the last loss terms. The embeddings are optimized by middle loss term, as shown here. Beta is selected to be 0.25 for the beta result. For more details, please check with these references. Thank you. Bye.